Hey everybody, welcome to the Chapter 8, Day 8 notes for AP Calculus. In this video, we're going to take a look at volumes with known cross-sections. So what that means is we're going to basically be finding the volume of a solid created with whose base is going to be the intersection of two functions. And then there's going to be a known shape for the cross-section. So in the picture given here, you essentially have this circular area which would be bounded by your functions, and then the cross sections of our solid are represented by this purple square. So essentially what that means is the square is the cross section, and when we integrate, we're going to use the area of the cross section in our integral. So we're going to use the area of the cross section in the integral. In terms of that formula. Now, with that being said, when you look at this cross section that's a square, the side length of the square is going to be determined by those functions that you're looking at. So whether we're doing it in terms of x and we're doing top minus bottom, or we might be finding that height in terms of y, where it would be right minus left. So it ties into how we find the area. I think it'll make a little bit more sense if we just get into the first example and take a look at it and kind of put it all together. So it says, consider the region R formed by the y-axis, the function y equals 4 radical x, and y equals 8. We want to find the volume of the solid with R as its base. Okay, so that shaded region is going to be our base. If the cross section taken perpendicular to the x-axis are squares. All right, so let's get an idea of what's going on. If we were to start by graphing the function, if we were to graph y equals 4 root x, all right, that's going to be a square root function that's going to look like this. And then if we were to graph the line y equals 8, the line y equals 8 is going to be a horizontal line that looks like that. And at some point, those functions are going to intersect. We would want to find that point of intersection. So, you can do that by setting these two equations equal to each other. That's one way to look at it. So if we said that 4 root x is equal to 8, then root x is equal to 2. And if we square both sides, x equals 4. So that just kind of gives you that this point is at 4, 8. Now, it did say that the region was bounded by the y-axis as well. So the shaded region that we are referring to is this shape here. All right, so that's that shaded region. That's the R value that the question is talking about. Now the volume that we are looking for is for the solid if the cross sections are perpendicular to the x-axis and they are squares. All right, so perpendicular to the x-axis means you've got these vertical slices here, and then that basically means our squares, and I'm not going to be a great artist here, but those squares are essentially coming out like this. Really they're coming kind of straight out to us, perpendicular to the x-axis. But the fact that they're perpendicular to the x-axis is what tells us that we're going to do everything in terms of x when it comes to integration. All right, now the formula for area of a square is side squared. So the area of the cross section is what we're going to use in the integral. So when we do this, what we're going to set up the integral is it's in terms of x, again because we're perpendicular to the x-axis. Our limits of integration are going to go from 0 to 4 because those are the x coordinates, or that is the x coordinate of our interception point. All right, and then we're going to integrate the formula for area of a square. So we have whatever the quantity squared. The side length, oops, I should probably get a different color. The side length of our squares, all right, that we're going to build together to create that solid, are going to be found by doing the top function minus the bottom function. That's how we're going to get this distance, which represents that side length. So the top function is 8, and the bottom function is 4 root x. So we have 8 minus 4 root x, and that's with respect to x. And that's the integral that we are going to set up to find the volume of the solid, whose base has this region and the cross sections are squares. All right, so kind of hard to maybe picture what that actually looks like. And I'm not a great enough artist to draw that for you, but this is the setup. All right, when we plug that in the calculator, this is the volume. All right, so let me pull up the calculator here. Let's go shift plus. We're going to integrate from 0 to 4. All right, and in parentheses, we have the function 8 minus 4 times the square root of x. That quantity is being squared, and we're integrating with respect to x. And we get 128 thirds, which as a decimal is about 42.667. So we get 42.667. And then this problem doesn't provide units, but because it's volume, this would be units cubed. So the pieces of this that you need to understand are, we're finding the volume for a solid with known cross sections. So we're going to use whatever the formula for the area of that cross section in our integral. Okay, that's the formula we're going to integrate. If the cross sections are perpendicular to the x-axis, then we're going to integrate from left to right, which is in terms of x. So our limits of integration are going to go from 0 to 4. And the side length of the square in this case is going to be found top minus bottom to get that distance. And that's the function top minus bottom that goes into our formula. All right, hope you guys found that helpful. Let's go ahead and take a look at example 2. It says the base of a solid is bounded by y equals x cubed, y equals 0, and x equals 1. We want to find the volume of the solid if the cross section taken perpendicular to the y-axis is a square. All right, I would encourage you to pause the video and try this on your own, paying close attention to that piece right there, meaning perpendicular to the y-axis. All right, so if we took a look at the graph of this function, just so we can kind of get a visual of what's happening, y equals x cubed, right, is going to be that cubic function. It's going to curve up here, curve down here. All right, we are also bounding that by y equals 0, which is the x-axis, and x equals 1, which is this line right here. That means that this area right here is the base of our solid. All right. This point of intersection right here is 1, 1. Now, we know that the cross sections are taken perpendicular to the y-axis. So that means they're going to be this direction, and they're also going to be squares. So again, area is s squared. All right, the fact that it's perpendicular to the y-axis, now we're going to have to integrate in terms of y, which means everything we set up is going to be done in terms of y. So our volume is going to equal the integral from 0 to 1, because those are the y values. The area formula is sides squared, and we're going to integrate with respect to y. Well, the other thing you have to remember is that when we integrate with respect to y, our functions have to be in terms of y, and we're going to go right minus left. All right, so the right function is that vertical line 1 minus. The left function is the cubic. Well, our equation y equals x cubed, that's in terms of x. So if we want to write this in terms of y, then we're going to isolate x, and x is the cube root of y, which you can write it as the cube root of y, or you could write it as y to the 1/3 power. Completely up to you of how you write that, but now you've got your integral. All right, you've got your area formula, which is side squared. You've got your function, which is right minus left, and now you can plug that in the calculator. So if we do that, let's go ahead and take a look at what we got. Whoops, it's the wrong thing. All right, we're going to shift plus. We're doing the integral from 0 to 1. And then we had 1 minus y to the 1/3 power. And that is being squared. And we're going to integrate that with respect to y. Hit enter, we get 1/10, which as a decimal is about 0.100. So 0.100. And the other thing you got to remember is we're finding volume, so it's going to be units cubed. So again, guys, when it's perpendicular to the x-axis, integrating in terms of x, everything is in terms of x. If the cross sections are perpendicular to the y-axis, then we're going to integrate in terms of y, which means everything needs to be in terms of y. Limits of integration and the functions. All right, let's go and look at a few more examples and see what we got going on. So example 3 says region R is in the first quadrant, formed by y equals 1/2 x squared and x equals 4. R is the base of a solid whose cross sections are rectangles drawn perpendicular to the x-axis, where the height of each rectangle is 3 times the base of the rectangle. Write an expression for the volume of this solid. All right, again, guys, pause the video, see what you come up with on your own. All right, we got a lot going on in this problem. Okay, now we've got cross sections that are rectangles. That means that our area formula is no longer going to be side squared. It's really base times height. All right. It is perpendicular to the x-axis. That's telling us that we're going to do everything in terms of x. But then we also have this piece here that the height is 3 times the base. So the height is 3b. All right. Let's go ahead and just draw a quick diagram of what this would look like so we can get a feel for our graph. All right, y equals 1/2 x squared. That's going to be a parabola with the compression by 1/2, so over 1 up 1/2 in both directions. Kind of missed mine. And then over 2 is normally going to be up 4, but if we do half of that, we're only going to go up 2 in both directions. All right, so we've got this parabola that's going to look like this. We've got x equals 4, which is this vertical line right here. All right, so basically what that tells us is that the base of our solid is going to be this area here. Now, this point of intersection, you might be able to figure it out, but the easiest thing to do, guys, really is to just set the equation. So if x is 4, we know that the x coordinate's 4, and then 4 squared is 16, half of 16 is 8. We can just plug that into the formula. So we have 4/8. Now, we are perpendicular to the x-axis. All right, so we're going to integrate from left to right. All right, and that's going to basically be how we get our formula. So if we look at this now, we're going to go ahead and set up the integral. So the volume is going to be the integral from 0 to 4. All right. The base, all right, is going to be the top curve, which is 1/2 x squared, minus the bottom, which is the x-axis, so 0. So really, it's just whatever the height of 1/2 x squared is. So the base is 1/2 x squared. And then the height is 3 times the base. So this is going to be times 3 times 1/2 x squared. Okay. So this piece right here is coming from the base, and this is the height. All right. Well, you could have earlier in the problem, and this would have actually been helpful, is taken your area formula and wrote it as b times 3b, which is simply 3b squared. And then that makes it a little bit easier, I think, in terms of setting up your integral, because you can always take the 3 out. So if we take out the 3, we're going to have the integral from 0 to 4. And then you just have 1/2 x squared times 1/2 x squared. So that's going to be 1/2 x squared squared. Anyways, all right. And again, we're just writing an expression so we don't have to solve it. So if we kept going in terms of simplifying this expression down, we've got 3 times the integral from 0 to 4. Well, 1/2 squared is simply 1/4. X squared squared is x to the 4th dx. And then you can always pull out the constant. So you've got 3/4 times the integral of 0 to the 4, or 0 to 4 of x to the 4th dx. And that right there would be an expression to find the volume of that solid. Okay. Clearly, if we wanted to know what that volume is, we could just plug it in the calculator and get our answer. All right. For example 4, we want to find the volume of a solid whose base is bounded by the circle x squared plus y squared equals 4, with cross sections taken perpendicular to the x-axis that are squares. All right, so let's just look at a few things. Cross sections perpendicular to the x-axis, and they are squares. So that means that our area formula is s squared. Perpendicular to the x-axis means we're going to integrate everything in terms of x. Well, if you draw the graph, you should hopefully understand that this is a circle with a radius of 2. That's what we got going on. So that's the area of our base. And we're going to basically be finding the volume of a solid whose cross sections perpendicular to the x-axis are squares. So we got these squares that are, coming out at us. Now, the way the equation is written, x squared plus y squared equals 4, that's neither in terms of x nor in terms of y. So what we are going to have to do is rewrite that so that it is in terms of x in this case, because we're perpendicular to the x-axis. That means solve the equation for y. So if we do that, y squared is equal to 4 minus x squared. And if you square root both sides, y is going to be plus or minus the square root of 4 minus x squared. So that's what it's going to look like. The top piece is the positive root 4 minus x squared, and the bottom is the negative 4 minus x squared. So when we set up the integral for volume, our limits of integration are going to go from -2 to 2. All right. We are squaring in this situation in terms of x. Now, you can come up with this formula inside the parentheses a couple of different ways. I mean, you really can stick strictly to the top minus bottom. And what that's going to look like is the square root of 4 minus x squared minus negative square root of 4 minus x squared. And you'll probably notice that negative negative adds positive, so the square root of 4 minus x squared plus the square root of 4 minus x squared is going to give you 2 square root of 4 minus x squared quantity squared dx. Some people will kind of think about the symmetry behind this and just know that, okay, if the top is the square root of 4 minus x squared, then I'm going to double it, right? But this really is technically how to get to that point. Without a calculator, we can simplify this expression down a little bit more to negative 2 squared is 4, and then the square root of 4 minus x squared is just going to be 4 minus x squared dx. You could then pull out the constant 4, and you've got the integral from negative 2 to 2 of 4 minus x squared dx, and go ahead and plug that in the calculator. So let's go ahead and do that and see what we get. Let's go shift plus. Oh, let me go out in front here real quick. So 4 times. And then we were from negative 2 to 2 of 4. Well, need parentheses here. So 4. Oh, no, I don't need the parentheses. Well, that's fine. 4 minus x squared dx. Hit enter. And we get about 42.667. Oops. It did not give us any units, so we're going to go ahead and go with units cubed as our volume. Now, what I'm going to do, guys, is just show you that you should get the exact same answer if we were to plug this integral into the calculator as well. So let's just do that real quick. So if we go shift plus from negative 2 to 2, all right, in that case, we had 2 times the square root of 4 minus x squared, quantity squared in that case, dx, and there's that 128 thirds, which is 42.667. So, you just got to be careful as you set up the equations in your functions. But, a key to this is knowing the shape of the cross sections so that you know which area formula to integrate. And you can really think about it as when you integrate area, you are finding volume. All right, so we got a couple other questions here we're going to take a look at. Example 5 is asking us to, well, it says let f of x equal 2x squared minus 6x plus 4. G of x is 4 cosine of 1/4 pi x. Let R be the region bounded by the graphs f and g. As shown in the figure, region R is the base of a solid, where each cross-section perpendicular to the x-axis is an equilateral triangle. Write but do not evaluate an integral expression that gives the volume of the solid. All right, again, pause the video, give it a shot, and then check out how we do it. All right, guys, so let's just kind of highlight a couple key things. We have cross-section is perpendicular to the x-axis. It is an equilateral triangle this time. All right, so the area formula for an equilateral triangle is s squared root 3 over 4. So that's the formula that we're going to ultimately integrate. All right. We got to know which function is top and bottom. So f of x is a positive quadratic. So that means that this bottom function is f of x and the top function is g of x. They're intersecting at 0, 4, and 2, 0. So that becomes important. All right. Our cross sections are perpendicular to the x-axis. All right, so vertical, we're going to do top minus bottom. All right, put it all together. We've got the volume is going to equal. It's the integral. Now we're integrating from 0 to 2. When you look at the formula, we've got s squared root 3 over 4. The root 3 over 4 is a constant. So we can pull that out in front. And then all that leaves us with is s squared with respect to x. Now, in this case, the side lengths are top minus bottom. So that is simply g of x minus f of x. And because all we had to do was write the integral expression, that's our answer. You know, it is important to remember when a problem defines what f of x is and what g of x is, you can refer to them by those names, f of x and g of x. All right, I hope you guys found that one helpful. All right, and you know, maybe got a quick little reminder about that formula of area of an equilateral triangle. And if we take a look at example 6, it says let f of x and g of x basically be the same two functions. R is the region bounded by the graphs as shown in the figure. Region R is the base of a solid where each cross section perpendicular to the x-axis again is an isosceles triangle, all right, with leg on R. Now, I think the intention of this problem, guys, is for it to be an isosceles right triangle with a leg on region R. So one of the legs is on region R, so you kind of have this leg here, and then it's coming out at us, and then the hypotenuse of the right triangle is going to be there. So just kind of keep that in mind. What that means is that the area of an equilateral triangle is going to be 1/2 base times height. And that's the area formula that we're going to ultimately integrate. But again, because this leg is in the region, that means that the isosceles triangle, the other leg is coming out here. That's going to be the height. So you can really think about this as 1/2 base squared because the base and the height are equivalent. All right, guys, pause the video, try to set up your integral and check it, see or compare it to what we get. All right, so what I'm going to do, we're going to set it up. We got volume equals the integral. Now we've got a constant, so we're going to go 1/2. We're going to do a quantity squared. Our limits of integration, again, in terms of x, are left to right. So that's from 0 to 2. And it's top minus bottom. So our top function was cosine. So again, we've got g of x minus f of x. And we're doing it in terms of x, so we have to end with that dx, and that's the answer. All right, guys, hope you found those questions helpful. Looks like we do have one more example with extra practice. I'll add the extra practice in a second video, so you guys can check those out if you want. But give them a shot on your own and see how you do, and I'll see you guys next time.